Hello everyone. So today's lecture is a continuation of previous lecture on transportation of natural gas. So let us recap quickly what we had gone through in the last lecture on transportation of natural gas. So when the natural gas is purified, it is ready to go to consumer in different form, like the natural gas can be transported through the pipeline in the form of LNG, CNG, GTL and others. We discussed based on the amount of the natural gas to be transported and the distance or terrain it covers, the appropriate mode of transportation can be chosen. We discussed in detail about the pipeline, briefly on the LNG, CNG and GTL. The infrastructure and market available for the natural gas is also one of the major factor that determines which mode of the transportation of natural gas should be chosen. If there is adequate infrastructure for LNG or CNG mode and the demand at the user side is significant at a local place or at a distance place, appropriate mode can be chosen. In the last lecture, we focus on transportation by pipeline, where we understood the pipeline system can be classified in three ways: gathering system, where the natural gas from different sources is gathering. This is from different wells, different gas processing unit. That is where this part should be chosen at an appropriate place where it is able to cover large number of the gas well in the same reservoir pool. Now, this should also have the facilities to accommodate the gas that is imported from other place or some other sources. Then it travels through this main trunk line, the big diameter pipeline, reach to a place from where it is distributed again through a small diameter pipeline to consumer. Consumer can be individual houses, industries or others. In between these two, the gathering station and consumer, it is not only the pipeline that is playing a major role for transporting this thing, other factors associate with the transportation of natural gas like the supply and demand, that should also be considered. For that, the storage facilities either in the depleted oil reservoir or in the LNG form in LNG plant facilities should also be designed as a part of pipeline design system. There are significant number of compressor to maintain the pressure or to maintain the throughput of the natural gas from one place to another place should also be considered. And to do that, in the last lecture, we started setting up the mathematical equation using the first law of thermodynamics. So, for a case of steady state one dimensional flow in the z direction from pressure P1 to P2, we could set up the mathematical equation, and that says the pressure drop in this pipeline is because of gravity, friction and kinetics, plus there might be shaft work and some other part. Certain terms can be dropped. We did for the case when the pipeline is horizontal, this is not contributing, constant area, constant diameter pipeline. So, the kinetic energy is also not contributing, and the simplification of this equation after considering how to calculate F, rho and EO, we could establish the relationship, that is how the desired relationship, that is Q is the function of pressure difference like P1 and P2, both the terms are appearing in the expression along with the dimension of the pipe and fluid properties. So, this is the standard equation. Depending on how we are substituting for this root of 1 by F, this is a transmission factor, we can get different form of the equation. And considering that, we could set up the equation like a Bamoth equation, Panhandle equation, Panhandle B equation. So, with this background of the last lecture, let us solve a problem where it is given a pipeline is designed to transport the natural gas from point 1 to point 2. The conditions are given, like the diameter of this pipeline is 10 inches and the length is 150 miles. The pressure at one end, the P1 point is 500 psia, and it is delivering the natural gas to other point, and the point where we are understanding the performance of this pipeline, the pressure at point 2 is 200 psia. So, a tube of 10 inches diameter, 150 miles long, is transporting natural gas. At one end it has 500 psi, another end it is having 200 psia. We can consider as the equation derived in the last class, considering no kinetic energy, no shaft work is being applied on the system, the constant diameter pipeline as well as under isothermal conditions, we can say the average temperature is also specified, and that is given is 80 degree Fahrenheit, that is equal to 540 Rankine. Base temperature, base pressure, those are appearing in this equation, we know. So, the TB base temperature can be chosen in the different units. So, let us say degree Fahrenheit it is 60, and converting it into degree Rankine it becomes 520 R. Similar for the base pressure, it is 14.7 psia. So, let us see what information is given and what we need when we are considering or predicting the gas flow rate in a unit of cubic feet per hour. And the expression we are having on the right hand side, big expression is there, and the unit are matched in such a manner, the QH will give us cubic feet per hour, or the desired unit of the Q that we want from this equation. Now, what others is not given? F, we will talk about this. P1 is given, P2 is given, T, the average temperature is given, length of the tube is given, gamma C is not given. So, we can say the gas that is getting transported from point 1 to point 2 is having certain specific gravity, let us say that is 0.7. So, now this information is also known to us. Now, it remains compressibility factor, diameter is also known. So, two terms remains, F and Z bar. So, let us talk about the Z bar. It is a compressibility factor. We understand from our natural gas properties class how to calculate compressibility. To calculate the compressibility, we need to know the average temperature and average pressure. Average temperature is given, we can assume the average pressure just taking this P average is equal to P1 plus P2 by 2, and when we do so, we can get the value of average pressure, that is 350 psia. Now, knowing the average temperature, average pressure, specific gravity of the gas, by using the method like the Brill and Bax method, we can calculate the compressibility factor. So, let us assume I did that calculation and got the value of compressibility factor as 0.9298. Now, the F remains in this expression, otherwise I can get the QH by putting every value in this expression. Now, question comes how to know the F. From the last class or the class on WPR, we understand the F depends on the roughness of the pipe. So, nothing is mentioned so far about what is the called roughness of this pipe. Let us say this information is also given to us, that is epsilon, the roughness of the pipe, that is equal to 0.0006, or not given, we can always assume this as one of the value. And next, to know the F, this friction factor, we can go to literature, and depends on the Reynolds number or depend on the flow regime, we can calculate either from the chart or from the expression given in the literature how to calculate the F value. To know the friction factor value, we need to know the Reynolds number to read the Moody's chart. Epsilon by d we can calculate, because epsilon given to us, d is the internal diameter of the tube. So, we can calculate epsilon by d. Now, Reynolds number, so let us see by the definition in the desired unit that we discussed in the last class, the Reynolds number expression appears like 0.48 gamma z q by mu d. Gamma z we know, q is in CFH, the unit we want in cubic feet per hour, mu is in centipoise and d is in inch. So, diameter is also given to us in inch, and based on that Reynolds number expression we will get the numerical factor because of adjusting the units for the parameters appearing in this expression. Now, question comes, gamma z is known to us, d is known to us, what about q, because we are supposed to calculate q, and what about mu, the viscosity of the gas that is being transported from point 1 to 2 through this pipe, which is having roughness 0.0006 and the pressure at one end is 500 psi, other hand 200 psi. We can calculate the viscosity of the gas knowing the average temperature and average pressure of the system. So, let us see, if I use that method of CKB, I got the value of viscosity as 1.34 centipoise. So, I know now viscosity. Now, Q is not known to me, and to know the Reynolds number, or next extent to know the F that is appearing in this expression, I need to know the Reynolds number. That is where the iteration is required, because we are going to calculate the value of Q with the help of Reynolds number, while Reynolds number depend on Q. For that we can do the iteration procedure. So, what we can say, let us assume some value of Q at first instant 500,000 is chosen the flow rate in CFH. After assuming this value, we can calculate now the Reynolds number value, and when we are calculating the Reynolds number, we can put in this expression of Jane in 1976, which is recommended for most of the turbulent flow conditions, where how to calculate the F, that is just depends on both roughness of the pipe or the relative roughness of the pipe, that is epsilon by d, and Reynolds number. So, now we know the relative roughness of the pipe, assuming the value of Q, we know the Reynolds number. After putting that Reynolds number in this expression and the epsilon by d value, I can calculate the value of F using this expression, and when it is done, I got some value of F. Now, this F should be put in the expression of Q, whatever the form we are taking, like Behmeth equation or other, that depends on this F. So, this is a general equation where the expression for F is not included, it is just calculated separately, and we had chosen this Jane 1976 model to calculate the F. Putting the F value along with other parameters, we know all them, we can calculate the new Q value. Now, match the Q value which is assumed is matching with this calculated value of Q or not. If not, then we can take, this is the next assumption, repeat the procedure, calculate the Reynolds number, this should be N R E capital, R should be there. So, we can calculate again the new Reynolds number value, new F value and Q new value, and we got this improvement. It is not 500,000, it is 664,000 plus. In the second round, it got improved to some new value. When we put this value in the third trial, perform the same calculation, got the another new value. Comparing this old and new, still there is a significant difference. We can go for one more iteration. Now, comparing these two values, the difference is only 9 CF per H. So, we can consider this okay, otherwise we can go for one more fifth iteration and to calculate the value of Q, and that is where the iteration procedure is required, because our F depends on Reynolds number and Reynolds number depend on Q, and we are calculating Q. So, after doing this thing, now we came to know what is the flow rate, that with that the gas is passing through this tube, that came out as 0.67 million cubic feet per hour. Similar exercise can be done considering the other expression for F, like what Baymouth had done. We can consider that equation of Baymouth also and calculate the QH value. In that, Baymouth is considered only diameter is responsible for calculating the F value, not the Reynolds number or not the relative roughness of the pipe. Some numerical coefficient appear in that expression that account for the relative roughness of the pipe as well as for the flow regime. If we do so, we can calculate the value of QH with the method of Baymouth. It is coming out as 0.6 million CFH. So, still there is a difference between the value which we calculated by iteration procedure or by Baymouth equation, but in a range of like 0.67 and 0.6, Baymouth equation is a good approximation, because we do not know this method is correct or not. For that, what we can do, we can go to Moody's chart and see the Reynolds number is varying in the range of 1.7 10 to the power 6. In that range, we see it depends on epsilon d also, not on the Reynolds number. So, both the expression, this expression consider the relative roughness, that is why it may be considered as relatively more accurate compared to Baymouth equation we are getting, and that is why this Gen 9076 model is recommended for the turbulent flow region, because it predicts how the F value is changing with respect to effective roughness as well as Reynolds number. With this example, it is clear how to set up the equation, how to perform the iteration to get the missing parameter. In this problem, it was QH itself, which was supposed to be calculated when the other conditions are given to us. In the last class, we could set up the expression for different form of pipeline equation, like the Baymouth equation, which consider how F is changing with respect to diameter only. Panhandle equation, it is not diameter alone, but it is in the form of Reynolds number. The expression is given, which was further modified and another expression given. Putting all these 3 F in the previous equation or in the general equation, we can get this expression. We could also write the empirical pipeline equation, that says in a general form you can write in this manner, where A1, A2, A3, A4, A5 could have some numerical value, and the numerical value are according to the equation. It is Baymouth equation, Panhandle equation or Panhandle B equation. So, with this background, let us start how to set up the line or pipeline system in series, parallel and looped manner. It is often required the throughput should be increased. Previously, for example, a particular place is having X demand. Now, the demand in that particular region is increased. How to modify the pipeline system, what design system or design approach should be chosen to meet that demand at consumer end. For that, either the entire pipeline system may be modified, or just the modification can be done in the existing pipeline system to meet the demand or to meet the throughput that can be transported from the existing pipeline system. This is required the setup of parallel, series or loop pipeline system, not only to meet the throughput, but for the cleaning purpose also. For the pipeline, those may go through pressure derated condition, means those become old and they cannot handle certain amount of the pressure. Maybe that portion of the pipeline or the pipeline in that region can be put in the loop or in series or in parallel condition to meet the throughput at the other end. So, a common economical solution is place one or more lines in parallel, either partially or throughout the line, to replace a portion of the line with a larger one. That can be done. So, the setting up in this manner either partially or fully, we can go with a series parallel and series parallel, that is called the combination, and it is named as a looped pipeline system. The general philosophy about setting up of the pipeline in series, parallel or in a loop manner involved in deriving the spatial relationship used in the solution of complex transmission system that express the various length and diameter of pipe in the system as equivalent length of common diameter. So, the equivalent length of the common diameter or equivalent diameter of common length, their equivalence means that both the line have the same capacity with the same total pressure drop. So, when we are setting up the series, parallel and loop pipeline system, because of different reason, meeting the throughput, considering the cleaning options, under the philosophy like the pressure at both the point should be maintained as well as the capacity should also be maintained. The equivalent length of common diameter or equivalent diameter of common length should be considered. In this case, what happens when we are changing certain part of the pipeline, we will see how by changing that portion, how the total flow rate or the capacity of the gas that can be transported will get changed. There could be n number of combination that can be set up. In previous case or example, we were having 150 miles long pipeline, we set up the mathematical equation to calculate the QH. Similar, between this 150 miles pipeline between point 1 and point 2, certain portion may be put up for the series and parallel. Common option is series parallel combination and increasing the throughput. This is required to meet the demand at the other end. So, let us understand how the series, parallel and loop pipelines are installed. So, for example, in the series, this is for the series pipeline system, where initially we are having the pipeline like this, which is having the diameter D1, pressure P1 at one end and pressure P2 at the other end. Or if I say pressure P1 at this end, point 1 of interest, and this point of interest 2 where the pressure was P4. So, maintaining the pressure P1 to P4 can be installed the pipeline in a series manner, where the part of this total length L is divided in segment, let us say in 3 segment L1, L2 and L3. So, this L2 part is replaced with higher diameter, let us say D2, and we are going to have the larger diameter pipe for this length segment L2. So, the L1 is just remains as the original pipeline, L2 segment is replaced by D2, and because of the diameter got changed, the pressure at the outlet of D2 will get changed, let us say it is P3, and similar at this point the another segment of this entire length L, that we can say L3, that segment is also replaced with a little bit more larger diameter tube. So, let us say this is D3 and the pressure at the end of is P4. So, when the single line was there, pressure was P1 to P4. Now, the size has been changed, the diameter has been changed at 2 locations or 2 segments L2 and L3. We are having the pressure distribution like this inside of it. This is a series combination where the capacity can be increased. In parallel case, what happens? We are having this total Q2 that is flowing between pressure point P1 to P2. Now, this pipeline of diameter D1 and Q1 was put under the parallel conditions. Between these 2 points, another pipeline of diameter D2 with a flow rate Q2 has been set up. And because of that, the flow rate in this pipe becomes Q1, and another pipeline is also installed parallelly Q3. So, we are having the 3 parallel pipeline system here, and conditions are maintained in such a manner P1 P2 is same. We want to see the capacity increasing because of putting the pipeline in parallel with two different diameter. Not necessarily the diameter of the new pipelines are always higher than the previous one, they may be the smaller diameter, D2, D3 may be the smaller diameter, but in complete parallel pipeline we are having the entire length L has been put in the parallel mode with the pipe of different diameter or the same diameter can also be there and with length L. While in the looping system, so this is D2 should be D2 and this is D3. So, initially a pipeline of D3 diameter, certain segment of that, let us say this is L1 segment has been transferred to parallel line option, where we are having the two parallel branches of different diameter D1 and D2. So, for all this combination we can say for a particular segment, let us say in a series this segment, again it is a pipe with relative roughness, with F value, the pressure difference is there, it is having the length, it is having the diameter, non-gas is getting passed through this section, we know the gamma z of that, we can calculate compressibility factor, we can calculate the viscosity also. So, now we can set up the equation for each segment that is appearing in all these combination. For example, here in series we can set up this equation. For simplicity we had considered the Baumol equation, but similar problem can be solved with Panhandle equation, either A or B or any other equation. The difference is in the form of F is calculated. So, let us see in series we can set up for this and this, each segment L1, L2, L3, similar we can do for the parallel and loop line. Let us understand one by one how we can do that. So, when the pipelines are in series, similar schematic diagram is here. The pipeline L1, which is the original pipeline, we are having the L2 and then we are having the L3, 3 segments, different diameter, different pressure drop, but the common point is here where both the different diameter pipes are getting joined, we are having the common pressure P2, similar here P3. So, for this case, first segment, second segment, third segment, all the informations are given to us. We can set up, let us apply the Baumol equation for each segment. For this pressure drop P1 to P2, we can set up this equation. This is the same equation, we just converted that from Q form to P1 square minus P2 square form. Just taking everything on the other side, we can set up that thing. The advantage is for each segment we can set up in terms of pressure. So, for segment 1 it is P1 to P2, everything is okay here, the only difference is diameter D1 and L1, others are same because QH is flowing from all this. Okay. Now, we are having this second segment 2 where the diameter is different, D2, length is different, L2, the pressure difference is 2 to P3. So, it is from P2 to P3, we can set up the equation like this. Similar we can do for the third segment. Now, when we can do this for 1, 2, 3 segment, we can do it for n number of segments, does not matter 2, 3, 4, 5, we understand how to set up the equation for each segment of length L1 and diameter D1, we can do the expression. Now, when we sum all these three, P2, P2 will cancel out, similarly P3, P3 will cancel out. So, this term will cancel out and we will left with P1 square minus P4 square on the left hand side. Right hand side, this is a common part that came out separately, this is also common part, temperature, compressibility, gamma z, that is not going to change with the diameter and length of the pipeline. This part will be different than the single segment equation that says the form of L by D. In the Baumol form, we are going to get the addition of L1 by D1 to the power 16 by 3, similar for L2, similar for L3 segment. Now, we can convert this back again the form we want, that is QH. After doing that, we will see we are getting this expression. This expression should also have Pb in the denominator. So, we are having the QH form when the segment of a pipeline are put in series. Now, we are having the equation Q also with us, that says, for example, the entire pipeline is just having this D1 diameter and spread for all L length. So, originally this was like this equation, and the pressure P1 was here, P4 was here, that is still there, P1 and P4. We can set up the equation for the same. Adjusting this equation is not required because we already having in the form of QH. Now, what we can do, we can divide Q by QH just to see how much gas capacity got increased by changing certain segment of the pipeline with a larger diameter. Here we have chosen D2 and D3 are larger than D1. If we divide this Q, that we can say QT with this Q1, we are going to get this expression. This expression says, on the numerator you are having some L and D, and in the denominator you are having the L and D for all three segments. Now, just to know how much gas capacity increase, we do not need to do all this calculation we did in the previous example, how to calculate compressibility factor, F value and other thing. We can just know how much segment of a original or existing pipeline has been replaced by the other diameter pipe. We can calculate the increase in the gas capacity. We will solve one problem to do that. Let us go with the parallel mode. In parallel mode, what happens? We are having this again P1 and P2 at one end and two end. We can set up the equation for this pipeline Q1, Q2 and 3. For each pipeline which is having the different diameter, different flow rate, we can calculate Q1, Q2 and Q3. Now, this Q should be QT, the total flow rate Qt can be calculated by doing the summation of all three pipeline flow rate. So, this is Q1, Q2, Q3. If we sum up, we get Qt is equal to Q1 plus Q2 plus Q3, and after doing the summation, we see the L is common in all three expression. This is just the diameter that is different. So, we are going to get the diameter in this form is getting summed up, because the different diameter pipelines are in parallel. The total Q should be depending on the diameter of the pipeline installed parallel to the existing one. Similar we can do to understand or to calculate how much increment is happen in terms of the gas capacity. We can divide this Q2 considering just Q1 is there. So, that is already we are having this expression. If we do so, we get this expression, and in this expression we see even the length is cancelled out, because all the three lines are occupying the entire length L of the existing pipeline, and it is just a matter what size of the diameter pipeline is installed in parallel to the existing one. That is going to calculate the increase that is going to be in the Q value. Now, when we are having a system where we are installing parallel as well as series option and calculating the increase or calculating the increment that is going to be in the flow rate, we can apply the similar principle of series and parallel here. So, for example, between these 2 points we are having the parallel combination, and for that we understand how to calculate the total flow rate, that is Q1 plus Q2 will tell us the total flow rate between pressure P1 and P3. So, here total flow rate is Q1 plus Q2, and that is between P1 and P3 pressure. After adjusting this equation, we will get this form, and in this form we are having this L1, and that L1 is here D1, D2 both are in parallel, they will go to denominator. So, this is the same mode as we did in the parallel line. Now, this system is in series with this L3 pipeline. Here is the L3 segment. So, we can set up again the Baumol equation for the third segment, and in this form we are going to get this P3 minus P2 equation. Now, we can replace this P3 square when we add up both the equation, the relationship between P1 and P2. So, this is P1, this is P2. So, between these 2 points P1 and P2, we are having the relationship which accounts for both series as well as parallel combination. If it is considered the parallel mode was not chosen, it is just a single diameter D3 pipeline that was originally here, we got this expression, and when we dividing the QT with the Q3, that is the original flow rate, if there is no pipeline is installed, we will get this expression. Again this expression will tell us how much increase can be expected or achieved when we had done this arrangement. Here this equation depend on both length as well as diameter, because it is having the combination of series and parallel. So, we can understand this with the help of one example that says a pipeline can be put in series, parallel and looped pipeline. There could be n number of options that we will discuss in the next slide, but for example, the pipeline is under consideration and this pipeline is having certain diameter and certain length. So, I can write the diameter, this is having 6 inches and the length from here to here, let us simplicity assume small length, this is 20 miles. Now, this pipeline is under consideration, we are not going to put other detail like what is the gamma z, what is the relative roughness, because those are not appearing when we are talking about putting the system under the calculation for calculating increase in gas capacity of the pipeline while we are installing series, parallel or loop pipeline system along with this one. So, let us say a pipeline of 20 miles with diameter 6 inches was subjected to consider series, parallel and loop system. We need to know the pressure at this end P1 and at this end P2, and here we are assuming the P1 and P2 are little bit far from both the compressor and delivery point. This is the segment which is not getting affected by the compressor or delivery point. This is just a segment of the pipeline or of the long pipeline which we counted as a 20 miles in the length and 6 inches in diameter. Knowing this pressure P1 and P2, the pipeline was subjected for series case. In this series consideration, the 5 miles of this pipeline, let us say 5 miles is taken out, and instead of that a pipeline of bigger size, let us say this is having diameter of 10 inches is installed. So, this is 5 ml 6 inches diameter has been taken out and the same length 5 ml with larger diameter 10 inches is installed here. We want to see the increase in the Q that is going to be by doing this arrangement. So, we are having the expression Q2 by Q1 here L original length, that is L is equal to 20, diameter D1 that is the original diameter that is 6 inches, and this all is in the same units. We do not need to worry about the converting into unit system. This is 20 miles. Now, L1 which remains after making the system under the series mode. So, we are having the L1 after taking 5 miles, it will be 15 miles, and L2, which is the next pipeline size, will be 5 miles. Now, what we can do, we need to know the diameter D2. We have this D2 is equal to 10 inches. Now, we have the expression, there is no D3, we had just did this segment in two parts, L1 and L2. When we put everything in this expression came from Baumol equation. When we put in this expression, we get the value of this expression as 1.1423. That says, after replacing the 5 miles pipeline of 6 inches diameter by the same length pipeline of 10 inches diameter, the increase in the gas capacity is 14%. There could be another possibility where we are saying parallel to this pipeline of 20 miles, another pipeline of 10 inches diameter is installed parallel to this. In this case, the length is same 20 and the diameter of the parallel tube is 10 inches. So, now let us look the parallel case, the pipeline design in the parallel mode. D1 will be same 6 inches, D2 will be 10 inches, there is no D3 we are having, and D1 is again 6 inches in the denominator. When we put in this expression, we can get the numerical value of this, and that comes out as 490. It means 390% increase in the gas capacity occurred when we put 10 inches diameter pipeline of 20 miles along with 6 inches diameter pipeline. So, large increase in the gas capacity can be expected because the diameter is large, so it is more than 390%. Looped pipeline system. So, instead of putting everything is in the parallel, what we can do, this is original pipeline of 20 miles long and 6 inches in dia. We can say a part of it is put under the looping system or under the parallel mode, and in that case let us take the same value, it is 5 miles that was put under the looping of 10-inch diameter. We know the expression for the looping system. Here L is again 20, D3 is the original diameter, that is D3 is equal to 6 inch, and D1 is equal to whatever the new pipeline has been installed, that is 10 inch. 5 miles is considered to put in the parallel mode, that is why it becomes the looping system. And when the calculation is performed, the quantity or numerical value comes out as 1.1467. It means 14.67% increase in the gas capacity is calculated when we have this kind of the looping system. So, I think with this example, it is clear how we can perform the calculation and calculate the gas capacity is changing when we are having the series, parallel and loop system. Not necessary, we are always going with a bigger size or always looking for a higher diameter size. It might be possible we can reduce the quantity that is transported by reducing the size of the diameter, but that is very rare case. Mostly it is we want to increase the gas capacity because day by day the demand at the other end of natural gas is increasing. With this example, I would like to go with the general expression for looped pipeline system. The general expression is required because every time if you are performing the calculation, that can be done with the help of a computer, but every time you have to choose the pipeline, you have to choose the length and diameter you are going to replace. Instead of that, the expression of the previous loop system can be put in a general form, where you can put different value of the length, different diameter, and can have a system or a graph where you are having the understanding of if this segment of the pipeline is replaced by this diameter, how much gas capacity increase can be done. And that could be a good exercise when you are given a task of designing the pipeline. You can consider several combination of that, and based on the economy involved or the cost involved in replacing the pipeline, an appropriate decision can be made. So, let us go in this expression which we had in the last slide for the loop pipeline system. Here L is the original length, L1 is the segment that puts in the looping system. The number of looping system we are having, we have to do it for each looping system. Let us go with one of the simplest case, where we are having the looping system, just only certain length of the existing pipeline has been put in the parallel with a different diameter D1. So, the original, it is having D3, now it is put in parallel with a diameter D1. So, the length of this is L1 and this entire length is L, and this length will be L3. Let us say with the same notation we are going. Now, this Qt by Q3 is equal to what? Q3 plus increment. Q3 is the original without any doing modification in the pipeline. Now, whatever the modification is done, that is here divided by Q3, and that modification or that the increment is happening in the gas capacity can be represented by a term, and that terms, let us say we are saying some P term, and this will be 1 plus P by Q3. It means this term represent the increase in the gas capacity. We can denote this with the general term used for this is X. We can say this Qt by Q3 is equal to 1 plus X. Similarly, the Y be the fraction of looped pipeline. So, how much pipeline segment has been put in the looping system, we can define Y is equal to here like L1 put under the looping system. So, L1 by L is my Y. And similar, we are having another segment here that says what about L3 by L. Simply L3 is equal to L minus L1 divided by L. So, we can write for this is 1 minus Y. Now, if we put for this x plus 1 and we can take this in the denominator, this term will not be there. Putting for Y, we can go further ahead with the expression or the desired expression we want. Here is another term appearing is R d, that is the ratio of the looping pipe diameter to the original pipe. So, here we had done the looping with D1 divided by the original diameter is D3, and this is represented by RD. So, when we are taking this in the denominator, L will get adjusted by the by, and ratio D1 by D3 will be adjusted by RD. If we put everything here, we are going to get this expression, and in the explicitly form of the x can be adjusted this equation, and we are going to get this expression in the form of x. I think it is clear. This can be written like taking the square root out of here, we will get Q2 by Q3 square, and then we are going to get x plus 1 square, that is appearing here. And similarly, I think this can be done as an exercise. You will get first this expression, after doing the adjustment you are going to get this expression in the form of x, and with the help of this expression you will get the relationship between x, y and R d. X represent the increase that is going to be in the gas capacity, y what part of the existing pipelines should be put in the looping, and R D the ratio of the diameter, means that segment which is put under the looping, what diameter should be chosen. We can put different value and can generate the result. As done in the book, I have taken this plot, and that says the effect of looped line on the increase of gas flow rate for various pipe diameter ratio. So, where it is done, different diameter ratio has been chosen. So, see here it is not always you are choosing the higher diameter, R D lesser than 1 means smaller diameter has been chosen. To understand the looping, means R D value higher means larger diameter is chosen. The increase in flow rate is plotted on y axis while considering how much length percent is put under the consideration. So, let us consider some of the case where we are having R D is equal to 1, means same diameter was put in the looping, and when we are having this diameter of the existing pipeline, similar diameter was put for entire length. Simple understanding is same diameter is put for the same length between this point to this point, the capacity should be doubled, and that we can see from here for R D is equal to 1, when 100% was put in the consideration, it is here where we are having the 100% increase in the gas capacity. And when we are having this parallel diameter at a lesser size, we are going to get the increment there, but not up to doubling the capacity, while the diameter of larger size which is used for the looping, we will always get higher. And that has happened in the previous example, when we put 10 inches parallel to 6 inches, 390% increase was obtained. This can also be done when different segment, not necessarily entire thing put in the parallel line, some part of it 10%, 20%, 30% is put under the looping system. We understand by seeing the expression or by common understanding, when the small part is put under the looping, the increment will be less. As we are increasing the part of the existing pipeline to be looped, the percent of gas capacity increase will be higher, and it goes like beyond even 200, 300. Previous example we had seen 390% also. Considering the other parameter, the path lines, the material of construction, the gas capacity which is required to be increased, the system can be chosen from such kind of the designing, and depend on the other factors, the existing pipeline can be put in the looping, or based on this the new pipeline can be laid out with the series parallel combination. With this understanding, I think it is clear how to use pipeline system to transport the natural gas from one place to another place, how to understand the relationship between flow rate, pressure, fluid properties, and the size of the pipe used. Now, further it is in series, parallel and loop pipeline system. Other parameters should also be considered when we are designing appropriate pipeline system. For example, material of construction is not considered, it is one of the mechanical properties that decide what type of the material should be chosen. It depends on several factors, the pressure the pipeline is going to experience, the terrain it is going to face, the climate it is going to pass through. The wall thickness is not considered, again several factors, the collapse criteria and other things, the material of construction decide the wall thickness, and the corrosion allowance is not considered. What we did is simply pipeline equation that give us the flexibility to calculate the gas capacity that can be increased to a desired level has been discussed in this class. Other mode of the transportation are also there other than the pipeline. For example, CNG and LNG depends on the source from where the natural gas is being transported to destination, means where it is going to be used. The path line it is going to face, it is onshore, offshore, it is having different political reason to pass, or other factor determine the mode of transportation other than considering the technical part. Pipeline design is still the first choice compared to others, but the other modes are also getting popular because of their own advantage. For example, CNG and LNG are also the mode of natural gas transportations, where CNG stands for compressed natural gas. In this state, the gas remains in the gas phase, but under very high pressure condition that varies up to 2000 to 3500 psi. In this pressure range, the gas is still in the gaseous mode. The temperature can be from 30 degrees C to minus 40 degrees C. Again, reducing the temperature, the more volume can be accommodated in the same vessels. Further reduction can be done in the temperature, but not up to the level where it is going to be converted into liquid form. And we can compress the gas by increasing the pressure to 2000 to 3000 psi. The compression ratio or the volume of the gas occupied in a vessels compared to under standard condition is 200 to 250 ratio. So, 200 to 250 times the gas can be compressed, and it will be in the gaseous phase only. There are several uses of compressed natural gas. So, for the sea transportation system, compressed natural gas is becoming a choice because it can be transported in a tanker kind of the system. Those are less costlier, and the compression ratio is not that high as compared to LNG, but the facilities required to compress the natural gas, transport the natural gas is more economical compared to LNG. If we reduce the temperature little bit more down, even the compression ratio can be improved. While in case of LNG, liquefied natural gas, the fluid is cooled down to certain temperature, that is around minus 163 degrees Celsius, and the gas get converted into liquid. It is not a chemical reaction something, it is just a phase transformation is happening. The gas is put under the refrigeration cycle, and it is going to be chilled or deep chilled, where it is going to in the liquid form. The pressure is ambient pressure or around 14.7 psi, temperature is minus 163 degrees Celsius, and under that condition, when it is going to be liquefied, the compression ratio is very high, 600. So, the 600 times natural gas can be stored in the same volume which is considered at standard temperature and pressure condition. That is the advantage of LNG, that why LNG is considered as a technology proven and safe, but both the processes are having their own features. For example, the compressed natural gas can deliver or can be chosen an option to deliver the natural gas when the small volume for the short distance is supposed to be transported, while the LNG is considered for a longer distance and large quantity is getting transported. CNG also need a special type of the tankers, sometimes they called in the sea transportation mode called the floating pipelines, while LNG, the terminals are required, the places are required where the natural gas can be liquefied. So, these LNG facilities are required, and then it's need very special type of the tanker through which it can be transported by maintaining the temperature minus 163 degrees Celsius, and at both the places, the source places from where it is getting transported to the place of receiving end, the facilities or the terminal facilities should be available to accommodate the natural gas transportation. So, both the modes of transportation like CNG and LNG depends on several other factors like the facilities, infrastructure available, the quantity supposed to be transported, how many rounds can be made, the loading and unloading facilities are available or not. Compared to CNG, LNG is still having a higher, significant higher share in the transportation. Actually, after the pipeline, LNG is the second choice, but because of the uses of CNG in different fields or in different sector, like for the vehicles, for the local transportation, the CNG form is being considered very significant option or prominent option. Another mode of natural gas transport could be converting natural gas to liquid. The process is called GTL. In this process, the natural gas, that is mostly methane, is gone through the steam reforming process or just a reforming process, depend on the oxygen source provided to this reforming process happen. It may be the steam reforming. The oxygen source can be just O2, can be steam, can be CO2 or can be air. So, the product of natural gas reforming are CO and H2, that is called the syngas. The CO and H2 can further go through the chemical process, that is Fischer-Tropsch synthesis, and can go through the polymerization reaction and can produce higher hydrocarbon compounds. Those higher hydrocarbon compounds are liquid at the ambient temperature and pressure condition, and along with those CXHY compound, H2O or CO2 or the source of oxygen gets released. The product CXHY can be upgraded further to have the desired product, that could be hexane, naphtha grade, diesel grade or waxes. There are other form of the liquid, those can also be produced from the natural gas, like DME, dimethyl ether, any additives that is used in the crude oil. So, the difference in the LNG and GTL is, in LNG there is no chemical reaction happen, just because of the temperature the gas is going to change its phase from gas to liquid, while in GTL process it is a chemical synthesis process or chemical conversion process with the help of catalyst and appropriate operating condition like temperature and pressure in a particular type of the reactor source of oxygen. We can convert this through reforming and further applying the Fischer-Tropsch synthesis process into the desired liquid compound. Research is still going on to make this process more viable, more economical, because it depends on the type of the reactor. Several reactor configuration like it is shown here, where we are having several channels. One of the channel is shown like this, and within this channel we are having this catalyst packing. Several type of the catalyst can be used. Nickel is considered as low cost catalyst compared to other, but better activity is observed with Ru and Rh. So, the catalyst plays major role in this type of the conversion, and lot of research is going on towards this direction to make GTL more economical and feasible. Other mode of the transportation can be converting gas to power. This is called the indirect mode, where electricity is generated with the using the natural gas, and natural gas is contributing to meet the energy demand. Even in the GTL process, there could be two ways, direct and indirect way. So, the direct conversion, we get low selectivity and low conversion, that is why it is not economical or it is not in the practice much, but in the indirect mode, this is the mode we just discussed. 3 steps are involved: reforming, Fischer-Tropsch synthesis. So, this is reforming, Fischer-Tropsch synthesis, and this is upgrading. So, the direct mode is different, and the indirect mode we are getting the liquid. It is not direct conversion to liquid, we have to perform some chemical reaction to get the conversion of gas to liquid. Other mode, gas to power, converting natural gas to electricity, gas to solid, crystalline form and gas to commodity, converting this into some commodity material and then transporting them by local transportation mode like the truck, rail and other mode. So, with this brief discussion of CNG, LNG and GTL, I would like to conclude the discussion on transportation of natural gas by different mode, and we had more emphasis on pipeline design system. With this, I would like to thank you. Thank you very much for watching the video. We will meet in the next lecture. Thank you.